तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we will continue with our discussion of the various properties of the Fourier transform. To start with, let us consider aspects related to energy. Suppose f of t be a voltage signal. Now, let us imagine that such a voltage is given to a 1 ohm resistor. Then, if f of t is a periodic signal, then the power dissipated in this 1 ohm resistor is from minus t upon 2 to plus t upon 2 of f square t dt, the average value 1 over t naught. This is called the power dissipated in the signal, or we often refer to as power available from f of t. Power available from f of t. So, irrespective whether the signal is a voltage signal or something else, normally we refer to this as power available from f of t. Of course, this will be quite appropriate if f of t is a voltage signal. Even otherwise, we can refer to this as a power available from the f of t. And this is a periodic signal, and we saw that this quantity, the power available from the signal, can also be obtained from the Fourier coefficients as n from minus infinity to plus infinity of Cn magnitude squared. This is a relation which we have already discussed when we talked about the Fourier series expansion of a periodic signal. Now, what we would like to see is how this concept can be extended in the case of a f of t which is not periodic. F of t is aperiodic, and we also assume that it has got a finite amount of energy in that, in the sense that minus infinity to plus infinity of f of t magnitude dt is finite. So, this is a restriction which we already imposed on finding the Fourier transforms of the various signals that we have considered so far, and we also assume that this is also true. So, if this is so, then when you divide by t naught, when t naught goes to infinity, then the power becomes 0. So, when we talk about aperiodic signals of this type, where the square of the integral is over the infinite band of frequencies, infinite time is finite, then there is no meaning in talking about power, because power becomes 0. So, all that we can do in such cases is only calculate the value of this integral f square t dt, and that has the dimensions of energy, because we are not dividing by t naught. So, this is energy in the signal is finite, is non-zero, energy available from the signal. So, when we talk about aperiodic signals, it would be more convenient for us to talk in terms of energy available from the signal. Therefore, we will have this particular heading for this topic, energy considerations. So, in the case of aperiodic signals we talk about energy available from the signal, where we talk about periodic signals we talk about power available from the signal. So, we would like to see what is the energy available for the signal in terms of the Fourier transform. So, the energy that is dissipated in this 1 ohm resistor is given by this. So, that energy in 1 ohm resistor energy dissipated in the resistor is minus infinity to plus infinity of f square t dt, and this I would like to write as minus infinity to plus infinity, t running from minus infinity to plus infinity, f of t, and for the other f of t I use the inverse Fourier transform formula, which is 1 over 2 pi omega from minus infinity to plus infinity f of j omega e to the power of j omega t d omega. This is the expression for the f of t. So, instead of writing f square t, I multiplied f of t by the another equivalent expression for f of t times dt. So, this has got two integrals, one on time domain and one in the frequency domain. What I would like to do is interchange the order of integration. That means, instead of integrating in the omega domain first and then later on the time domain, I would like to reverse the roles. I would like to integrate this expression in terms of time domain first and then in frequency domain later. So, if I do that, then I want to integrate in the frequency domain at the second stage. So, I will put this outside, and all terms involving omega and which do not involve time can be brought outside. Therefore, f of 1 over 2 pi will come out, of course, f of j omega will come, and the rest of the terms are f of t e to the power of j omega t, and of course d omega will also be outside, and you have dt f t e to the power of j omega t. These are the terms that are left. So, in the time integration from t minus infinity to plus infinity, I have f of t e to the power of j omega t dt. Now, let us look at this. If it had been f of t e to the power of minus j omega t dt, it would have been straight away f of j omega. But instead of minus j omega t, we have plus j omega t. Therefore, this whole expression now becomes f of minus j omega. So, this can be written as 1 over 2 pi omega from minus infinity to plus infinity f of j omega d omega, and this quantity is f of minus j omega. And as we already observed that for real functions of time, where f of t is a real function of time, f of minus j omega is the conjugate of f of j omega. Therefore, this will become 1 over 2 pi omega from minus infinity to plus infinity of f of j omega magnitude squared d omega. So, the power available, the energy available from the signal is given in time domain in this fashion, in frequency domain in this fashion. Now, f of j omega squared magnitude squared can be thought of as energy density. What it means is, around a band around omega, if we consider a small band of frequencies delta f, f j omega squared times delta f is the energy concentrated in that band centered around omega. So, this energy density is expressed in terms of joules per hertz per cycle per second. So, in a small band of frequencies centered around omega, this will be f j omega squared magnitude squared df, which is delta omega by 2 pi, is the energy available energy in a band delta omega centered around omega. So, if you take a small band of frequencies centered around omega, small delta omega, this is the energy that is available. All we have to do is therefore to find the total energy, you have to sum up all such energy say quanta in different bands, and that becomes this integral, that becomes 1 over 2 pi minus infinity to plus infinity of f of j omega magnitude squared d omega. So, this is an interesting relation that f of t, this of course is minus infinity to plus infinity of f square t dt. So, you can calculate the energy in time domain as minus infinity to plus infinity f square t dt, that is the energy, that is called the energy available from a signal f of t. You can also calculate the energy available from the signal in frequency domain in this fashion. F j omega squared is energy density, energy available for cycle per second. So, you have to multiply by frequency d omega by 2 pi, and integrate over the whole range of frequencies, you get the total energy that is available from the signal. These relations, relation for the periodic case and this relation for the aperiodic case are usually referred to as Parseval's relations. It is also occasionally referred to as Plancherel's theorem, particularly in the case of the aperiodic case. So, the Parseval relation in the case of a periodic signal is in terms of the Fourier coefficients. In the case of an aperiodic signal is in terms of an integral involving the energy density f of j omega magnitude squared d omega. To summarize the discussion here, when you talk about an aperiodic signal with a finite amount of energy, then you can't talk about the power available from the signal, which is going to be 0, because the base is T naught is going to be infinity, the average power over a complete time period is 0. We can talk about only energy, and the total energy available from the signal can be computed in two ways, one in time domain in this fashion and one in the frequency domain. The meaning of this is, if this is a voltage signal and this is given to a 1 ohm resistor, this is the energy that is dissipated in that 1 ohm resistor. You can calculate it in the time domain or frequency domain as the case may be. Now, let us work out an example to illustrate this particular concept. Take this example. We have f of t is e to the power of minus a t u t. Now, we would like to calculate the energy content in the signal, energy available from the signal in two ways, time domain. Do it in the time domain, energy available from integral from minus infinity to infinity of f square t dt, that is minus infinity to plus infinity of e to the power of minus 2 a t dt, but this lower limit is not correct because f square t exists only from t equals 0 to infinity. Therefore, you have to write substitute here from 0 to infinity e to the power of minus 2 a t dt. Therefore, this will become e to the power of minus 2 a t divided by minus 2 a evaluated between 0 and infinity. At the upper limit, this is going to be 0 because we are taking to be a positive quantity, and at the lower limit, of course, this is 1, this will become 1 over 2a. So, 1 over 2a joules is the total energy available from the signal. Let us work this out in the frequency domain. f of j omega is 1 over j omega plus a. But we were talking in terms of energy, therefore energy density is f of j omega magnitude squared is 1 over omega squared plus a squared, so many joules per cycle per second. So the total energy available from the signal is the 1 over 2 pi times the integral from minus infinity to plus infinity of 1 over omega squared a squared du. And this can be shown by substituting omega, put omega as a tan theta and carry out this integration, and you can show that this is indeed equal to 1 over 2a. Which is exactly the result that we have obtained earlier. If you plot f of j omega squared versus omega, the energy density is a function of frequency omega, you will get a curve like this. So this is the energy density. So this gives us an idea of where the energy is concentrated, at what frequency bands there is more energy. Now as you can see, there is a lot of energy in the low frequency band centered around the DC. At higher frequencies the energy is somewhat less. This additional information is obtained through the Fourier transform analysis as compared with the time domain analysis. Let us see how such a concept can be made use of in practice. Let us assume that this particular f of t, which we had, this exponential signal, is put through a low pass filter and we get an output signal f naught of t. This low pass filter has a characteristic like this: h of j omega magnitude a low pass filter essentially allows all frequencies up to a certain point and then shuts off all other frequency components. So let us imagine that our low pass filter here has a cutoff frequency equal to a and minus a. In other words, in the spectrum that is available for the given f of t, all frequency components having a magnitude omega greater than a become 0. That means h of j omega we are talking about the transfer function or the system function relating f naught of t and f of t is equal to 1 for omega less than or equal to a and 0 otherwise. So essentially what we are doing is, this low pass filter is such that it cuts off all frequency components beyond a certain value a. So if this is a and this is minus a, as far the output is concerned, f naught of t, the corresponding energy density f naught of j omega squared would be the one which contains frequency components within this band only. That means it will have only this minus a to plus a, the rest of the terms being cut off. And so suppose I want to know what is the energy available from f naught of t, then you have to take the same function but integrate between minus a to plus a rather than from minus infinity to plus infinity. So we have the energy available from f naught of t equals the integral of 1 over omega squared plus a squared, that is the energy density into times d omega over 2 pi. The integral now is from minus a to plus a instead of from minus infinity to plus infinity, and then by making use of the standard substitution that omega equals a tan theta, this can be shown to be 1 over 4a joules. It means that out of the total energy available from the input signal Ft, which is 1 over 2a joules, 1/2 of that energy resides in the band, frequency band omega from minus a to plus a. So, since when signals are transmitted through linear systems like a low pass filter, and these systems are characterized quite nicely in terms of the system function h of j omega, and if you would like to find out the properties of the signals that come out of the system or the response of the system, then frequency analysis in this manner turns out to be a very convenient tool, because these filters like this are characterized in terms of their frequency response, not in terms of their time response, and therefore the energy available from the f naught t can be more conveniently handled in terms of frequency characteristics of the signal, in terms of the spectrum as shown here. If we wanted to do the same analysis in terms of time domain, then it would be much more difficult, because you have to characterize the filter in terms of its time response, which can be done, but it is much more complicated. So, this example illustrates how we can utilize the energy concepts also in finding out the characteristics of various signals. Okay. So far we have been talking about signals with a finite energy content and signals which are absolutely integrable over the infinite range of time from minus infinity to plus infinity. You might recall that I mentioned earlier that we can extend the concept of the Fourier transform to signals which are not absolutely integrable over the infinite range, and in particular I mentioned that signals like u of t, a DC term, sin omega ct, cos omega ct, such functions also admit Fourier transforms, provided we use impulse functions which are justified from the theory of distributions in mathematics. We would now like to familiarize ourselves with some of the operational rules involving such functions. We will not go into the deep mathematical details of this. We will just assume some results and use them to derive the Fourier transforms of signals whose energy content is not necessarily infinite, or which is not finite. So, to start with, we would like to have some useful relations. We have discussed earlier this function sin theta by theta. This will have a variation like this with an amplitude 1, and this will be pi, this is minus pi. Sin theta versus theta. We are interested in the value of the integral of such a quantity. Suppose we say 0 to theta of say sin alpha by alpha d alpha. Such an integral is referred to as sine integral of theta. This is given the symbol SI of theta. Sine integral of theta is sin alpha by alpha from 0 to theta, and the variation of this is pronounced as sine integral of theta versus theta would be something like this. Asymptotically it reaches a value which is equal to pi by 2. So, this is a relationship which we will assume. That means, if you start from this point and go on integrating, it reaches a value pi by 2. That means, the integral, the area under this curve starting from theta equals to 0 theta to theta equals infinity will be pi by 2, which it is easy to remember this particular value, because if you take this triangle, this is pi, this is 1, the area of the triangle is pi by 2. So, the area of this triangle is pi by 2, and that is also the area under the curve from 0 to infinity, which means that the rest of the area, this one and all add up to 0. The positive areas are cancelled out by the negative areas, and therefore, the area under the curve of sin theta by theta from 0 to infinity equals pi by 2. So, we have the relation therefore, 0 to infinity of sin theta by theta d theta equals pi upon 2. Now, sometimes we would like to have, instead of theta we have sin a theta by theta d theta 0 to infinity. Now, if a is positive, then certainly you can say d of a theta by a theta, then this is the same relation as this, and the limits are not interchanged, therefore, this will also be equal to pi by 2, because a theta can be replaced by another variable x. But if a is negative, then no doubt d a theta by a theta, a can be cancelled out, but if a is negative, instead of plus infinity you have minus infinity, and you know sin theta by theta is a even function of time, but you are integrating in the negative direction, therefore, it will be minus pi by 2. So, the result is this value is pi by 2 for a greater than 0 equals minus pi by 2 for a less than 0. Or in other words, if you extend the sin theta, sin integral theta in the negative direction, it will be like this, and it reaches minus pi by 2 eventually. This is a relationship which is useful for us in our work. Just to illustrate this particular rule, let us consider an example once again. Find inverse Fourier transform of AD sin omega d upon by omega d upon 2. We know the result. We know that sin omega d upon 2 by omega d upon 2 times AD is a Fourier transform of a pulse function of amplitude A and width d centered around the origin. But we would like to find this out independently. So, let us do this. So, f of t would be 1 over 2 pi, and I take out this d by 2 outside, therefore, it will be 2a by t, 2a by 2a, integral from minus infinity to plus infinity of f of j omega, which is sin omega d upon 2 divided by omega d e to the power of j omega t d omega. That is the inverse Fourier transform of this function. This I can write as a upon pi minus infinity to plus infinity sin omega d upon 2 cos omega t dt d omega plus minus infinity to plus infinity sin omega d by 2 sin omega t d omega and a j sin in front, j sin in front. Now, this also by omega will continue to have here. What you observe here is, as far as the second integral is concerned, sin omega d upon t divided by omega, this is an even function of omega, this is an odd function of omega, and you are integrating between symmetrical limits from minus infinity to plus infinity. So, the contribution of this integral from minus infinity to 0 would be exactly equal and opposite to the contribution that arises from 0 to infinity. So, since this entire function is an odd function of omega and you are integrating between symmetrical limits, this goes to 0. So, what we have left with is only this, and this can be written further as you have sin theta and cos theta, therefore, you can combine these two as sin alpha plus beta plus sin alpha minus beta type of formulation you can make. Therefore, I can write this as a by pi, and then you have 2 also will come in because you are going to express this as sin alpha plus beta and sin alpha minus beta. So, you have sin of omega t plus d by 2 divided by omega, that is d omega, and minus infinity to plus infinity of sin omega d by 2 minus t by omega d. So, you have 2 such terms. Okay. Now, we can also observe here, first of all, before doing this, before going further, that this is an even function of omega, this is an even function of omega. Therefore, whatever integral you get from minus infinity to plus infinity would be twice the value of the integral which you would have got if you extended, if you integrated this from 0 to infinity. So, I can write this further as 4a upon pi, then 0 to infinity and 0 to infinity here also, that also I can write this here. So, I will do that. Let me see. Yeah. Okay. Now, I think this should be corrected. First of all, since I am doing the integration from 0 to infinity, I should have 2a upon pi, but sin omega t d by 2 sin omega d by 2 minus t will give me 2 times sin omega d upon 2 to cos omega t. Therefore, I must divide by 2 further. Therefore, this will finally become a upon pi. So, a upon pi, this integral from sin omega t plus d upon 2 by omega and sin omega d by 2 minus t omega. Suppose I call this integral I1 and this integral I2. And let us see what their values would be for different values of t. For this, I make use of this relation here. Sin a theta by theta d theta will be pi by 2 for a positive and minus pi by 2 for a negative. Therefore, if I plot I1, the value of I1, we have sin omega something by omega d omega, something very similar to this, and instead of a, I have t plus d upon 2. So, as long as t plus d upon 2 is positive, it is pi by 2. As long as t plus d by 2 is negative, it is minus pi by 2. That means this value of this integral will be like this. This is pi by 2, this is minus d, this is t, and this is minus pi by 2. So, as far as I1 is concerned, it will have a positive value of pi by 2 for t greater than minus d, so that t plus d by 2 is greater than 0, and as long as t plus d by 2 is negative, it has minus pi by 2. That is the value of I1. Value of I2, again the same formulation should be used. We have sin omega by omega d omega, but omega is multiplied by d by 2 minus t. Look at this expression again. Sin a theta by theta d theta is pi by 2 for a positive, minus pi by 2 for a negative. So as long as d by 2 minus t is positive, then it is pi by 2, otherwise it is negative. That means as long as t does not exceed d by 2, then it is going to be pi by 2, otherwise it is minus pi by 2. So as far as this will be the relation that you get finally as far as I2 is concerned. So what do you have got for when you add I1 plus I2? Now we no longer need this. So if you add I1 and I2, add up these two things, then this positive area will be cancelled by the negative area here and here. So you will be left with a pulse like quantity which will have a value of pi by 2 and pi by 2. This is pi by 2, this is minus pi by 2, therefore this is pi, and this lasts from minus d to by 2 to plus d by 2. Yeah, I should have put here, because I have a t plus d by 2 and t minus d by 2, I should have written here minus d upon 2 and this also plus d upon 2. Right. Therefore, this pulse extends from minus d by 2 to plus d upon 2, and therefore this is the value of I1 by I2. Therefore, you multiply by a by pi, so f of t would be a pulse of width a lasting from minus d by 2 to plus d by 2, a result which we would have expected from this. So what we have really done is, we know in the forward direction, if this is the pulse, this is the Fourier transform. We demonstrated its validity in the reverse direction, making use of the relation of this sine integral as the argument goes to infinity. Illustrated this because we might like to use this type of formulation later on in our further work. To discuss cases where the Fourier transforms involve impulses, let us see the origin of this trouble if we follow the classical rules. So let me say this some troublesome integrals. We have just now seen an example where in the forward direction we have got a pulse and then we found out the Fourier transform. When we went in the reverse direction, we had to work a little hard to get at the final pulse function. Let us consider another example. We know that delta t has for the Fourier transform equal to 1. Let us find the inverse Fourier transform of this one. We should be able to get delta t. How do we do it? Then we write for the inverse Fourier transform of 1 over 2 pi minus infinity to plus infinity of 1 e to the power of j omega t t omega. And when you try to integrate, you have some difficulty because you have got infinite limits. So in any case, let us see what this really means. So minus infinity to plus infinity of cos omega t plus j sin omega t d omega. And once again, sin omega t is an odd function of omega, and we are integrating between symmetrical limits. So we know the contribution from this goes to 0. Contribution from this goes to 0. So we can write this as 1 over 2 pi minus infinity to plus infinity cos omega t d omega. And once again, since cos omega t is an even function of omega, we can write this as 1 over pi and take the limit from 0 to infinity of cos omega t d omega. Now 1 over pi cos omega t d omega, so far so good, but if you try to integrate, you get minus sin omega t by t, and then when you try to substitute for omega infinity, then you do not know what that amounts to. So this type of integration does not lend itself to analysis by the classical methods. However, since we started with the inverse Fourier transform of 1, the inverse Fourier transform must lead to delta t. We know delta t has this Fourier transform. So apparently this whole thing must be equal to delta t. This must be equal to delta t. Now that is where we have a problem with the classical mathematics, and after the impulses came to be used in analysis of systems, then after their usefulness is recognized, mathematicians have developed a branch of mathematics called the theory of distributions, with the help of which the analysis of the mathematical methods using impulses are put on a more rigorous basis. But we will not go into that. We will, however, make use of certain results of that and put them down here, so that we will use them for our further work. Basically then, we have some important results which I will list them out, and these results which we will make use of in our future work. First of all, limit as t tends to infinity of sin omega t by omega will be pi delta omega. It can be explained on the following basis. Sin omega t by omega, how will it look like? So this will be equal to t, the height equals t. And the first 0 occurs when omega t equals pi, or t equals pi by, or this is sin omega t by, this is with respect to omega, or omega equals pi upon t. Now inquire as what happens when t becomes larger and larger. When t becomes larger and larger, sin omega t by omega, the function becomes this is pi upon t. So this first loop becomes smaller and smaller, but the height goes up. And we have already seen that the area under this curve of this is, as far as for the positive side is concerned, the area equals pi by t times t into half, therefore this is pi by 2, and on the other side is pi by 2. That means the area under this curve is pi. The area under this curve is pi no matter what t you use. So as the area from minus infinity to plus infinity of this is pi, and as t becomes larger and larger, this loop shrinks, and then you have a very large amplitude, and the first loop becomes 0. That is essentially the character of an impulse. And since the area under the curve is pi, then it is an impulse of value pi, and the impulse is situated at omega equals 0, because that is where you have a spike. So we can justify this on this fashion, in this fashion, that sin omega t by omega as t goes to infinity tends to the limit pi delta omega. Similarly, we can have 0 to infinity of cos omega t d omega equals pi delta t. That you have seen from this. We have earlier come to this. We got into difficulty 0 to infinity cos omega t d omega. What is it? What does it mean? It's pi times delta t. We did not know how to derive this, but we can assume this relation. Similarly, we have 0 to infinity cos omega t dt. After all, we have changed the variables here. This must be pi delta omega. And two more relations are useful. 0 to infinity sin omega t dt equals 1 over omega, and 0 to infinity sin omega t d omega is 1 over t. We assume these relations in our work when we derive the Fourier transforms of functions whose energy content is maybe infinite, may not be finite. So, these 4 relations are important for us. We will take this to be true in our further work. Okay. We will make use of this, as I said, in our further work, but just as an example we will consider just one particular case. Let us take a simple example now to illustrate this these relations. We will take f of t to be a DC quantity equal to 1 for all t. So, that means f of t is a constant 1. F of j omega for this is obviously from minus infinity to plus infinity of f of t e to the power of minus j omega t dt. Now, e to the power of j omega t can be written as cos omega t minus j sin omega t, and once again we can make use of the symmetry relation, and the cos sin omega t term will be this minus infinity e to the cos omega t minus j sin omega t dt, because f of t happens to be equal to 1. And the contribution of this will be 0 because it is an odd function and we have symmetrical limits. Therefore, I can write this as only integral involving cos omega t. Now, I take from 0 to infinity of cos omega t dt, and I introduce a 2 sign because 2 here, because instead of integrating from minus infinity to plus infinity, I am integrating 0 to infinity. And now, cos omega t dt integral from 0 to infinity is pi delta omega according to what we had already seen. Therefore, this is 2 pi delta omega. So, the Fourier spectrum for this is f of j omega. You have an impulse of magnitude 2 pi at DC. This is what we should expect. This is a pure DC term. Therefore, you have only a DC component here and no other components, and at the DC we have a finite amplitude for the voltage. Therefore, you have an impulse function. That means we are no longer, even though we are talking about coefficient density now, this coefficient density is infinite because there is a definite non-zero amplitude at DC. Therefore, the coefficient density is going to be infinite and it has got a magnitude equal to 2 pi. We will develop this theme further when we take about other periodic signals. So, in this lecture, therefore, what we have done so far is we started with the concept of energy in a periodic signal. We said when we talk about a periodic signal with finite energy, it is no longer fruitful for us to talk in terms of power because the average power over infinite interval goes to 0. Therefore, we can talk only in terms of energy available from the signal, and what we mean by energy available from the signal is if this signal is a voltage signal, if it is given to a 1 ohm resistor, what is the total energy dissipated in that 1 ohm resistor from minus infinity to plus infinity is what we call the energy available from the signal. And this energy available in the signal resides in different frequency bands by different amounts. Therefore, we saw that if we integrate from minus infinity to plus infinity, the energy density which is given by f j omega squared, integrate it with reference to omega and divide by 2 pi, because this energy density is in terms of frequency in hertz cycles per second, that will give you the total energy. And this we said is also referred to as Parseval's theorem. Then we discussed the possibilities of extending the Fourier analysis to signals whose energy content is not finite, and in that context we started with some interesting relations involving sin theta by theta functions, and we familiarized ourselves with sine integral, and then we put down some results here which are sanctified by the distribution theory in mathematics, which we cannot prove by classical methods. We assume these results, and making use of these results we tried to find out the Fourier spectrum of a pure DC quantity and came up with the result which is quite perhaps could have been quite obvious, that this particular signal has only one frequency component, and that is a DC, and therefore you have only one, the lines, it becomes a line spectrum once again in the Fourier transform also, but the coefficient, there is a coefficient which is non-zero, therefore the coefficient density has got to be infinite, therefore we have a delta function and the coefficient density is 2 pi delta omega, and the density occurs at 0. And so we can expect that when we talk about periodic functions, in the line spectra, the magnitudes are going to be infinite involving delta functions. More about this in the next lecture.